Hashtag the search for another world. Are we alone? Imagine this. Right now, at this very moment, somewhere 40 light-years away from us, on a planet shrouded in a dense atmosphere, something incredible might be happening. Perhaps it's raining there. But not ordinary rain made of water, rain of liquid methane, streaming down the slopes of mountains composed of frozen ammonia. Or perhaps, in an ocean tens of kilometers deep, beneath an impenetrable shell of ice, something is moving. Something alive. Or perhaps not. Perhaps there's absolute, dead silence. This is the paradox that has haunted humanity for decades. We live in an era when new worlds are discovered every single week. Every week. Planets orbiting distant stars, worlds so diverse and so alien that even the wildest imagination of science fiction writers from the last century seems pale compared to reality. And yet, silence. Why are we alone? Or are we not alone, but simply don't know how to listen? This is the story of the greatest mystery of our time. About how we're trying to find traces of life where it seemingly cannot exist. About biosignatures, these ghostly fingerprints of living organisms, imprinted in light that travels through space and time. About the revolution in astronomy that has completely changed our understanding of the universe over the past 20 years. And about why the answer to the question, "Are we alone?" might turn out to be nothing like what we expect. There was a time, and it ended not so long ago, when we were certain. Certain that we knew where to look for life. Certain that life must look a certain way, must breathe certain air, must swim in certain water. We were naive, like a child who thinks the entire world ends beyond their backyard fence. In the 90s of the last century, when the first exoplanets began to flicker in the data from our telescopes, the scientific community had a clear picture of what a habitable planet should look like. It was a picture drawn from the only known sample, Earth. And why not? After all, Earth works. Life here thrives, filling every crack, every corner, from the deepest ocean trenches to the highest peaks. It seemed logical to assume that life on other worlds would follow the same rules. Imagine Earth as the perfect recipe. Take one medium-sized star, not too hot, not too cold. A yellow dwarf, like our Sun, place a planet at just the right distance from this star, not so close that water boils away, and not so far that it freezes solid. This zone, this magical belt of space around a star, received a name that now every schoolchild knows, the habitable zone, or Goldilocks zone. Not too hot, not too cold, just right. Add to this recipe an atmosphere. Not just any atmosphere, but the right atmosphere. Nitrogen and oxygen in the correct proportions. An ozone shield protecting from deadly ultraviolet radiation. Greenhouse gases in moderation to maintain comfortable temperatures, but not too much, lest the world transform into a scorching hellscape like Venus. And, of course, water. Liquid water. This was the mantra, the sacred incantation of astrobiology: follow the water. Where there's water, there's life. Water is the universal solvent, the cradle of biochemistry, the medium in which molecules can dance their complex dance, creating and breaking bonds, generating what we call life. This concept was beautiful in its simplicity. It was elegant. It gave us a clear target: find Earth-like planets in habitable zones around Sun-like stars, planets with atmospheres containing oxygen and water vapor. Find them, and we'll find life. Or at least places where life could exist. But the universe, as it turned out, hadn't read our textbooks. The first exoplanets discovered in the mid-90s were monsters. Hot Jupiters, gas giants, massive as Jupiter, but orbiting so close to their stars that their surfaces are heated to thousands of degrees. Worlds where diamond rain falls, where winds blow at the speed of sound, where one side of the planet eternally faces its star, scorched by its light, while the other is plunged into eternal night. These planets were so far removed from our Earth, so alien, that it seemed impossible to find anything in common between them and our home. But this was only the beginning. The beginning of revelations that would overturn all our preconceptions. With each year, with each new discovery, the picture became more complex, more intricate. We found planets that by all parameters should have been lifeless deserts, but which, according to some models, could have conditions for life. We found moons of gas giants hiding beneath icy shells oceans deeper than all Earth's seas combined. We discovered planets orbiting red dwarfs, stars so dim and cold that it was previously thought life there was impossible. And slowly, very slowly, understanding began to dawn. What we considered the universal recipe for life was merely one variant among an infinite multitude. Life, as it turned out, can be far more inventive than we thought. Far more stubborn. Far more strange. Think about life on Earth. For a long time, we thought we knew its boundaries. We knew where life could exist and where it couldn't. Too hot. Life impossible. Too cold. Same thing. Too much pressure. Too little oxygen. Too much acid. In each case, the answer was obvious: life cannot be there. And then we found them. Extremophiles. Organisms that laugh at our limitations. Bacteria living in the boiling springs of Yellowstone at temperatures above 100 degrees. Microbes thriving in frozen Antarctic lakes where temperatures drop below -50. Archaea inhabiting the ocean floor near black smokers, hydrothermal vents where temperatures reach 400 degrees and pressure exceeds atmospheric by hundreds of times. We found bacteria in nuclear reactors, surviving radiation levels that would instantly kill any other known creature. We discovered microorganisms in deep underground mines, in complete darkness, where they live by feeding on minerals and the chemical energy of rocks. We found life in acid lakes where pH is so low it would dissolve metal. In salt ponds where salt concentration is 10 times higher than seawater. In desert soil where not a drop of rain falls for years. Each such discovery was a blow to our confidence. Each expanded the boundaries of the possible. If life on Earth can thrive in such incredible conditions, what does this say about the possibility of life on other planets? It says we underestimated life. Seriously underestimated it. And here we stand, on the threshold of new understanding. Before us lies a universe full of planets. Billions of them. Trillions. Planets of all sizes, all temperatures, all compositions. Rocky planets and gas giants. Ice worlds and lava hells. Planets with dense atmospheres and planets with no atmospheres at all. Worlds orbiting young stars and ancient ones, around solitary stars and binary systems. And the question is no longer whether life exists there. The question is, how do we find it? How do we recognize its traces in the light that reaches us from the depths of space? How do we distinguish a biological signature from a geological one? How can we be certain that what we're seeing is truly a sign of life, and not just a quirk of chemistry or physics? These are questions without simple answers. But they are questions we must answer. Because somewhere out there, in the ocean of stars and planets, perhaps right now, another form of life exists. Another intelligence. Another civilization that may be asking the same questions, looking at their night sky. Or, even more troubling, perhaps not. Perhaps we truly are alone. And that answer, in some sense, is even more frightening. What is a biosignature? This question sounds simple, but the answer contains all the complexity and all the beauty of modern astrobiology. A biosignature is a trace. A fingerprint. An echo of life, captured in data we can measure. Imagine a detective arriving at a crime scene. The perpetrator is gone, long vanished. But the detective isn't discouraged. He knows that every action leaves traces. Fingerprints on glass. Fabric fibers on chair upholstery. Shoe prints on the floor. Each of these traces tells a story. Tells about who was here, what they did, where they went. Astrobiologists are detectives of cosmic proportions. And biosignatures are their clues. Only instead of fingerprints. They search for molecules in the atmospheres of distant planets. Instead of shoe prints, changes in the spectrum of light. Instead of fabric fibers, reflection patterns that might indicate the presence of liquid water or vegetation. But how can you search for signs of life on a planet that's 40, 50, 100 light-years away? A planet we can't even see directly, which is merely a tiny point of light lost in the blinding radiance of its star. The answer lies in the very nature of light. Light isn't just illumination. Light is information. Each photon, each quantum of light carries within it the story of its journey. When light passes through a planet's atmosphere, it interacts with gas molecules present there. Each molecule, each atom absorbs light at specific wavelengths, leaving its unique signature in the spectrum. It's as if every chemical element, every compound had its own barcode, written in the language of light. And we've learned to read this language. The method is called spectroscopy, and it's one of the most powerful tools in the arsenal of modern astronomy. When a telescope captures light from a distant planet, or more precisely, light from its star that has passed through the planet's atmosphere, we can break this light into components, like a rainbow appearing after rain. And in this rainbow, in this spectrum, we can see dark lines and bright bands, each telling us about the presence of a specific molecule. See an absorption line at a certain wavelength? This might be oxygen. Another line. Water vapor. Yet another. Methane. Or carbon dioxide. Or ammonia. Or something else from the infinite variety of chemical compounds that can exist in a planet's atmosphere. But how do we distinguish a biological signature from a non-biological one? How do we know that the oxygen we detected was produced by living organisms and not geological processes? How can we be sure that methane is the result of bacterial activity and not volcanic eruptions? This is the greatest mystery, the greatest complexity in searching for biosignatures. Because almost any molecule that can be produced by life can also be produced by non-biological processes. Nature loves to create the same molecules through different pathways. Take oxygen. On Earth, the overwhelming majority of atmospheric oxygen is produced by photosynthesis, the process by which plants, algae, and some bacteria use sunlight energy to convert carbon dioxide and water into organic compounds, releasing oxygen in the process. This is the biosignature par excellence, the gold standard we'd like to find on other planets. But oxygen can form through other pathways. Ultraviolet radiation can split water molecules in the upper atmosphere, releasing oxygen. This process, called photolysis, can create significant amounts of oxygen without any biological involvement. Especially on planets orbiting active young stars that bombard their worlds with intense ultraviolet light. Or methane. On Earth, methane is produced in enormous quantities by living organisms, from bacteria in swamps to cows in pastures. This is another potential biosignature. But methane can also be released by volcanoes, can form through geothermal reactions in planetary depths, can be a remnant of the primordial atmosphere inherited from the planet formation process. See the problem? Each individual molecule can have both biological and non-biological origins. Each clue might be a false lead. But, and this is a critically important, but, the combination of molecules can tell us far more than any of them individually. This is the key insight that changed our approach to searching for biosignatures. We no longer look for one magic molecule, one unambiguous sign of life. Instead, we search for patterns, combinations, chemical signatures that would be extremely difficult or impossible to explain without the presence of life. For example, on Earth the presence of large amounts of oxygen in the atmosphere together with methane creates what chemists call thermodynamic disequilibrium. These two molecules react with each other, and in an equilibrium system they couldn't coexist in significant quantities. The fact of their joint presence indicates that something is constantly replenishing their supplies. And that something is life. Plants produce oxygen, bacteria produce methane, and these two gases exist in our atmosphere at concentrations impossible without biological processes. This is called a disequilibrium signature, a combination of molecules that is itself a sign of life. Not one molecule, but the interaction between them. A chemical signature that screams, something unusual is happening here. Processes are at work that disrupt the expected chemical equilibrium. But even this doesn't give us 100% certainty. Even disequilibrium signatures can have alternative explanations. Even the most convincing combinations of molecules could, in principle, be produced by exotic geological or atmospheric processes we don't yet fully understand. And here we arrive at an uncomfortable truth: there's no such thing as an absolute, 100% biosignature. No single test that could give us a definitive answer. Instead, we work with probabilities, with levels of confidence, with accumulated evidence. It's like assembling a puzzle. One piece might tell you nothing definite. But the more pieces you find, the more they fit together, the clearer the picture becomes. One molecule, interesting. Two molecules in a disequilibrium combination, very interesting. Add to this certain patterns in the planet's surface reflectivity, indicating possible presence of liquid water or even something resembling vegetation. Add seasonal variations in gas concentrations that could be linked to biological cycles. Add all this together, and the probability that you're looking at an inhabited world becomes higher and higher. But it never reaches 100%. Not from a distance. Not without direct study. And this is perhaps the most agonizing part of this entire enterprise. We can find all the signs of life, all the clues, all the hints, and still not be absolutely certain. Not without a mission that goes there, not without a probe that passes through the atmosphere, not without a rover that crawls across the surface. And yet we continue searching. Because even a probabilistic answer, even a tentative maybe, would change everything. Would change our place in the universe, our understanding of life, our philosophy of existence. There's another aspect of biosignatures worth attention. These are so-called surface biosignatures. Imagine you're looking at Earth from a distance of tens of light years. You don't see details, no cities, no roads, no individual trees. But you see light reflected from the planet's surface. And in this light there are patterns. Continents reflect light differently than oceans. But most interesting of all, vegetation. Plants have a very specific reflection spectrum. They absorb red light for photosynthesis but reflect significant amounts of infrared radiation. This creates a characteristic red edge in the spectrum, a sharp increase in reflectivity at the boundary between red and near-infrared ranges. This red edge is one of the most intriguing potential biosignatures. If we saw it in light reflected from a distant exoplanet, it would be a strong indication of the presence of something like vegetation. Of the presence of photosynthesizing organisms covering a significant part of the planet's surface. But, of course, there are caveats here too. Minerals can also create sharp changes in the reflection spectrum. Rust, for example, certain types of clay, volcanic rocks, all have their characteristic spectral signatures. Distinguishing a biological, red edge, from a geological imposter won't be easy. And one more thought that should make us pause: all these biosignatures we're searching for are based on what we know about life on Earth. We search for oxygen because Earth life produces oxygen. We search for methane because Earth organisms produce methane. We search for the red edge because Earth plants create the red edge. But what if life on other planets works differently? What if there are forms of life that use completely different biochemical processes, produce completely different molecules, create completely different signatures in light? What if we're looking at the wrong things? This is a disturbing possibility. The possibility that we could miss signs of life simply because that life is so different from ours that we don't even know what to look for. It's like searching for fish knowing only birds, or searching for flowers having concept only of fungi. But there's also an encouraging side. Some biosignatures might be universal. Some chemical processes are so fundamental, so efficient, that any form of life, regardless of its origin or biochemistry, would likely use them. Take water. Yes, life could exist in other solvents, in liquid ammonia, in liquid methane, even theoretically in sulfuric acid. But water possesses unique properties that make it exceptionally good as a solvent for biochemistry. It can dissolve a wide range of substances while remaining relatively stable. It exists in liquid form across a wide temperature range at atmospheric pressure. It participates in numerous biochemical reactions. Therefore, while we can't rule out the possibility of life based on other solvents, there are good reasons to believe that water-based life might be most common. And this is good news for us because we know how to search for water. We know what it looks like in spectra, how it behaves, where it can exist. Or consider carbon. Carbon is the basis of Earth biochemistry. Every known form of life is built on carbon compounds. And this isn't by chance. Carbon is unique among elements in its ability to form long, stable chains and complex three-dimensional structures. It can bond with a huge variety of other elements, creating molecules of incredible complexity. Could another element replace carbon? Silicon is often mentioned as a possible alternative. It has similar electronic structure and can also form chains. But silicon compounds are far less stable and far less diverse than carbon compounds. Silicon-based life is theoretically possible, but it would probably be far more limited, far less adaptive. So again, we have reasons to believe carbon biochemistry might be universal. Not because it's the only possible option, but because it's probably the best option. The most efficient. The most flexible. And this gives us hope. Hope that even if life in other worlds turns out strange and alien, even if it functions on principles we don't yet understand, there will still be some universal signs. Some common features. Some biosignatures we'll be able to recognize. Because ultimately life isn't just a collection of molecules. Life is a process. A process of extracting energy from the environment, using that energy to maintain complex organization, reproducing itself, evolving, adapting. And this process, however it's implemented, whatever molecules it operates with, must leave traces. Must create patterns. Must disrupt chemical equilibrium. Must be visible to those who know where to look. When the first exoplanet orbiting a sun-like star was discovered in 1995, it was like discovering a new continent. No, it was more. It was discovering a new ocean. A new world of possibilities. The planet was called 51 Pegasi b, and it completely shattered all our expectations. It was a hot Jupiter, a gas giant, massive as our Jupiter, but orbiting so close to its star that its year lasted only 4 days. 4 days. On Earth, that's the time it takes for milk in the refrigerator to still not spoil. And there, a complete revolution around the star. The surface temperature of this world exceeded 1,000 degrees. The atmosphere was most likely dispersed into space by stellar wind. If there were clouds, they'd consist not of water vapor but of vaporized metals and silicates. Iron rain. Glass snowflakes flying sideways in hurricane winds at speeds of several kilometers per second. This was a world from a nightmare. Or from science fiction. But it was a real world, orbiting a real star, just 50 light-years from us. And this was only the beginning. Over the past 30 years, we've discovered more than 5,000 exoplanets. 5,000. And each is unique. Each tells its own story about how planetary systems form, how they evolve, what incredible diversity is possible in the universe. We found planets orbiting binary stars, planets with 2 suns in the sky. Like Tatooine from Star Wars. We found rogue planets drifting in interstellar space without a star at all, dark and cold worlds illuminated only by the faint light of distant galaxies. We found planets whose orbits are so eccentric they spend part of the year practically on their star's surface and another part in the icy outer reaches of the system. We found super-Earths, rocky planets more massive than Earth but lighter than Neptune. Worlds that don't exist in our solar system but which turned out to be one of the most common types of planets in the galaxy. What are they like? Enlarged versions of Earth with even stronger gravity, even deeper oceans, even denser atmospheres. Or something completely different. We found mini-Neptunes, worlds sized between Earth and Neptune, covered in thick hydrogen atmospheres. Beneath these atmospheres could hide anything. Oceans of water under enormous pressure. Oceans of more exotic liquids. Or perhaps directly beneath the gas shell lies a scorching rocky surface heated by warmth trapped by the dense atmosphere. We found planets we call lava worlds, planets so close to their stars that their surfaces are molten. seas of magma spewing rock vapors into the atmosphere. Worlds where stone rain falls, where the sky glows from the heat of the molten surface, where the concept of day and night might not make sense at all because one side of the planet always faces the star, constantly melting under its merciless light. We found planets around red dwarfs, the most common stars in the galaxy. These stars are much cooler and dimmer than our Sun, but they can live trillions of years, far longer than the current age of the universe. Planets around red dwarfs must orbit very close to their stars to receive enough heat. So close they're probably tidally locked, one side always facing the star, the other always in darkness. What would life be like on such a planet? On the star-facing side, eternal day, constant warmth, but also constant bombardment by stellar flares. On the dark side, eternal night, cold, perhaps even frozen atmosphere. But between them, on the terminator, on the eternal boundary between light and darkness, there could exist a narrow zone of moderate climate. A ring of habitability encircling the planet. Could there be life there? We don't know. Red dwarfs are known for their activity. They regularly emit powerful flares, streams of X-ray and ultraviolet radiation that could strip atmosphere from a close planet. But maybe a sufficiently massive planet with a sufficiently powerful magnetic field could protect itself. Could retain its atmosphere. Could, possibly, become home to life. And there's another type of planet that excites astrobiologists' imaginations more than almost any other. Water worlds. Planets completely covered by ocean. Not just planets with oceans like Earth, where water covers 70% of the surface. No, we're talking about worlds where water is all there is. Where there's no land at all. Where the ocean might be hundreds of kilometers deep. We don't know for certain if such planets exist. But mathematics says they should be there. If a planet forms far enough from its star, where there's plenty of ice, and then migrates inward to warmer regions, all that ice will melt. And if there's enough ice, the result will be an ocean planet. What would life be like on a water world? There'd be no photosynthesis as we know it because sunlight couldn't penetrate hundreds of kilometers of water. But at the bottom of this ocean, under monstrous pressure that would make Earth's deepest trenches seem like a shallow puddle, there could be hydrothermal vents. Black smokers similar to those we find at the bottom of Earth's oceans. And around these vents, in absolute darkness, feeding on chemical energy erupting from the planet's interior, life could thrive. On Earth we know life exists around hydrothermal vents. Entire ecosystems independent of sunlight, based on bacteria that get energy from chemical reactions. Meter-long worms, blind shrimp, strange fish, all living in the eternal night of the deep ocean, in conditions that would kill most other Earth organisms. If this is possible on Earth, why couldn't it be possible on a water world? Why couldn't a biosphere exist there, even richer, even more diverse, based on the same principles? And most amazingly, we can detect such worlds. We can determine if a planet has a deep ocean by studying its density, its spectrum, perhaps even seasonal changes in its atmosphere that might indicate a global water cycle. But planets in other solar systems are only part of the story. In our own solar system, right under our noses, there may be places where life exists. Europa. Jupiter's moon, covered with a thick layer of ice. But beneath this ice, according to data from space probes, lies an ocean of liquid water. An ocean that might be twice as deep as all Earth's oceans combined. It remains liquid thanks to tidal heating, the gravitational influence of Jupiter and other moons that literally squeezes and stretches Europa, generating heat in its interior. And where there's liquid water, where there's an energy source, there might be life. Enceladus. Saturn's tiny moon, only 500 kilometers in diameter. But from cracks at its south pole erupt geysers, fountains of water shooting hundreds of kilometers into space. The Cassini space probe flew through these geysers and discovered in them not only water but organic molecules. The building blocks of life, erupting from a subsurface ocean. Titan. Saturn's largest moon, the only moon in the solar system with a dense atmosphere. But this atmosphere consists mainly of nitrogen with methane admixture, and surface temperature is minus 180 degrees. Methane rain falls there. There are methane lakes and rivers. It's a world where methane plays the role that water plays on Earth. Could there be life there? Life based not on water but on liquid methane. This seems incredible. Chemistry in such cold conditions proceeds incredibly slowly. But maybe, just maybe, organisms exist there that have adapted to these conditions. That live and reproduce at a pace that seems geological to us but is normal for them. We have no answers. Yet. But we have missions. Spacecraft now being planned or already built that will fly to these worlds, land on their surfaces, dive into their oceans. That will search for signs of life right there, on location. And if they find something, if they discover even one bacterium, even one sign that life exists or existed on another planet or moon in our solar system, it will change everything. Because if life arose twice in one star system, it means life isn't a rare miracle. It means it's common. It means the universe must be full of life. In every solar system where suitable conditions exist. On every planet or moon with liquid water and an energy source. It would mean we're not alone. Never were alone. And never will be. But how can we study worlds located tens and hundreds of light years from us? How can we analyze atmospheres of planets that are merely tiny points of light lost in the blinding radiance of their stars? The answer lies in technology. In the instruments we've created. In telescopes that look deeper and see more clearly than anything astronomers of previous generations dreamed of. Imagine the task. You need to see a firefly circling a searchlight. But not just see it, you must distinguish individual colors in that firefly's glow, determine the chemical composition of its light. And all this from a distance of 1,000 kilometers. Impossible? That's what people thought 20 years ago. And today we do it. Every day. This is what modern telescopes do when studying exoplanets. The first exoplanets were discovered not through direct observation but through their effect on stars. The method is called radial velocity. A planet, orbiting around a star, pulls the star with it through its gravity. The star wobbles slightly. This wobble is minuscule, a few meters per second, the speed of slow walking. But it creates a Doppler effect in the star's spectrum. The star alternately approaches and recedes from us, and wavelengths of its light correspondingly compress or stretch. We can measure this with incredible precision. And from these measurements we can deduce the planet's existence. Its mass, its orbit. Without seeing the planet itself. Only through its gravitational influence on the star. This was brilliant. This opened the door. But the method had limitations. It was most sensitive to massive planets on close orbits, hot Jupiters. That's why the first discovered exoplanets were such monsters. Not because such planets are most common, but because they're easiest to detect with this method. Then came the transit method. If a planet's orbit is aligned correctly, the planet will pass in front of its star when viewed from Earth. This is a transit. And during transit, the planet blocks a tiny fraction of the star's light. For an Earth-sized planet transiting across a Sun-like star, the brightness decrease is about 1/100%. 1/100%. But modern detectors can measure this. The Kepler Space Telescope, launched in 2009, observed more than 150,000 stars simultaneously, tracking their brightness with incredible precision, looking for these tiny dips that would betray a planet's presence. And it found them. Thousands. Kepler discovered more than 2,500 confirmed exoplanets and several thousand more candidates awaiting confirmation. It showed us that planets aren't just common, they're everywhere. Practically every star has planets. And many of these planets are in habitable zones of their stars. But Kepler did more than just count planets. The transit method allowed us to do something amazing. During transit, part of the star's light passes through the planet's atmosphere, if the planet has an atmosphere. And this light carries information about the atmosphere's composition. Remember spectroscopy? Each molecule absorbs light at specific wavelengths. When star light passes through a planet's atmosphere, molecules in that atmosphere imprint their mark on the spectrum. By comparing the star's spectrum during transit with the spectrum outside transit, we can isolate the component coming from the planet's atmosphere. This is transmission spectroscopy. And it's our main tool for studying exoplanet atmospheres. The first exoplanet atmospheres were studied back in the early 2000s. These were hot Jupiters with bloated atmospheres full of water vapor, sodium, other elements. But technology continued to improve. And then came James Webb. The James Webb Space Telescope, launched in late 2021, is a marvel of engineering. Its primary mirror has a diameter of 6.5 meters, 6 times the area of Hubble's. But size isn't the only advantage. Webb observes in the infrared range, in the region of the spectrum where many molecules of interest to astrobiologists have their strongest signatures. Infrared light is thermal radiation. Everything warm radiates in the infrared. Planets radiate in the infrared. And critically, their radiation isn't completely overwhelmed by their star's light in this range, as happens in visible light. Webb can do things previous telescopes could only dream of. It can study atmospheres of Earth-sized planets. It can search for traces of water vapor, carbon dioxide, methane, ammonia. It can determine atmospheric temperature profiles, search for clouds and haze, study what we call weather on exoplanets. And already in its first months of operation, Webb began making discoveries. It detected carbon dioxide in a hot Jupiter's atmosphere, the first unambiguous detection of this molecule on an exoplanet. It studied the atmosphere of a planet in the TRAPPIST-1 system, a system where 7 Earth-sized planets orbit a cool red dwarf, and at least 3 of them are in the habitable zone. TRAPPIST-1. This system deserves special mention. It's only 40 light-years away, by cosmic standards, our nearest neighbor. 7 planets, tightly packed on orbits that would all fit inside Mercury's orbit if we transplanted them to our solar system. They're so close to each other that from one planet's surface, Others would appear not as points of light but as disks visible to the naked eye. You could distinguish details, continents, if they existed. This is a system that fires the imagination. If one of these planets had a civilization, they could easily travel to neighboring worlds with technology not much more advanced than our own. They could colonize not one but several planets in their system. But is anyone there? Is there any life there at all? First data from Webb didn't detect a thick atmosphere on one of the studied TRAPPIST-1 planets. This was disappointing but not conclusive. Perhaps this particular planet has no atmosphere because it was stripped by stellar flares. But other planets in the system haven't been fully studied yet. Research continues. And Webb is only the beginning. Even more powerful telescopes are being built and planned on Earth and in space. Extremely large telescopes. Giant segmented mirrors capable of collecting hundreds of times more light than any existing instrument. The European Extremely Large Telescope. Primary mirror 39 meters in diameter. 39 meters. That's longer than a blue whale. This mirror consists of nearly 800 individual segments, each precisely aligned and controlled by an active optics system correcting even the tiniest deformations thousands of times per second. With such an instrument we'll be able not only to detect biosignatures in exoplanet atmospheres but to directly image these planets. See them as separate points of light distinct from their stars. Study light reflected from their surfaces. Search for seasonal changes that might indicate biological activity. There are also plans for next-generation space missions. Telescopes with special coronagraphs and star shades, devices that block the star's light, allowing the dim planet beside it to be seen. It's like an artificial eclipse created in space to make visible what's usually invisible. One concept is called the Habitable Worlds Observatory. A space telescope specifically designed to search for biosignatures on terrestrial planets in habitable zones of sun-like stars. Its goal, to study dozens, perhaps hundreds of such planets, create a catalog of habitable worlds, assess how widespread life is in the universe. And there are even more ambitious proposals. Telescopes on the Moon's far side, protected from Earth's radio interference. Space interferometers, multiple telescopes flying in strict formation, their light combined to create an image with resolution equivalent to a kilometer-sized telescope. With such instruments we could not just detect planets, not just study their atmospheres. We could map their surfaces. See continents and oceans. Distinguish changes in vegetation cover by seasons. We could, in principle, see evidence of civilization. Cities illuminating a planet's night side. Changes in atmospheric composition indicating industrial activity. This sounds like science fiction. But it's scientific fact. Or at least scientific possibility. The technologies exist. The physics is understood. It's a matter of engineering, funding, political will. And while these giant projects are planned and built, work continues with existing instruments. Each year brings new discoveries. Each year the boundaries of the known expand. We live in a golden age of exoplanet astronomy. In an era when the question, is anyone out there, for the first time in human history transitions from the realm of philosophy to the realm of empirical science. We can get an answer. Not in 1,000 years. Not in 100 years. Perhaps in the coming decades. Perhaps even sooner. But let's pause for a moment. Let's think about what we're searching for. What is life? This seems like a simple question. Everyone knows what life is, right? You're alive. I'm alive. The tree outside the window is alive. A stone isn't. But try to give a precise definition. Try to draw a clear line between living and non-living. And you'll discover it's surprisingly difficult. Is a virus alive? It reproduces, evolves, has genetic material. But it can't reproduce on its own, it needs a host cell. It has no metabolism. Many biologists don't consider viruses alive. There's something on the boundary, something between chemistry and biology. What about prion? They're just misfolded proteins, but they can reproduce by forcing other proteins to adopt the same incorrect shape. They cause diseases. They evolve in a certain sense. Are they alive? And crystals? They grow. They have structure. They can even contain defects that spread through the crystal like mutations. But no one considers crystals alive. See how quickly everything becomes blurred. The traditional definition of life includes several criteria. Life is organized, it has structure at different levels, from molecules to cells to organisms. Life has metabolism, it extracts energy from the environment and uses that energy to maintain its organization. Life grows and develops. Life reproduces, creating copies of itself. Life responds to the environment. Life adapts and evolves, changing across generations. This is a good list. But even it has problems. A mule, a hybrid of horse and donkey, can't reproduce. Does this mean a mule isn't alive? Of course not. Fire has metabolism, burns fuel, grows, reproduces, sparks create new flames, responds to environment, wind, humidity. Is fire alive? No. So what distinguishes life? Maybe it's not a set of properties but a process. Life is what happens when chemistry reaches a certain level of complexity. When molecules begin organizing into systems that can maintain themselves, copy themselves, evolve. When chaos of random chemical reactions yields to order directed by information. Information. Maybe that's the key. Life on Earth is based on information encoded in DNA. This information is copied, transmitted, sometimes altered. It directs protein synthesis that performs all cell functions. It's the blueprint, the recipe, the program. But must life use DNA? This is another question that torments astrobiologists. DNA is an incredible molecule. It's stable. It can store enormous amounts of information. The double helix can separate, each strand serving as template for creating a new copy. It's elegant. It's efficient. But is it necessary? Could life use a different molecule for storing information? RNA, a simpler precursor to DNA, can perform many of the same functions. There's the RNA world hypothesis suggesting early life on Earth was RNA-based, and only later did evolution invent DNA and proteins. Or maybe something even more exotic. On Titan, Saturn's moon, where liquid methane plays water's role, there could exist molecules that store information in a completely different way. Polymers built not from nucleotides but from some other monomers stable in extreme cold conditions. This is pure speculation, of course. We have no evidence of such exotic biochemistry. But we also have no evidence against it. And this is the problem when searching for biosignatures. How can we search for what we can't even imagine? The answer is to search for universal signs. Signs that would be true for any form of life, regardless of its specific biochemistry. One such sign is thermodynamic disequilibrium. Life, by its nature, fights against entropy. The second law of thermodynamics says closed systems tend toward disorder, toward equilibrium. But life creates order. It concentrates molecules. It builds complex structures. It maintains difference between an organism's internal environment and external environment. All this requires energy. Life must constantly consume energy to maintain its non-equilibrium state. And this leaves a trace. A planet's atmosphere with life will contain molecules in combinations that can't exist at equilibrium. This is exactly what we see on Earth with oxygen and methane. Another universal sign, homochirality. This is a complex word for a simple concept. Many molecules can exist in two mirror forms called chiralities or isomers. Like your left and right hands, they're similar but not identical, one is the mirror reflection of the other. Amino acids, protein building blocks, come in two forms, left-handed, L forms, and right-handed, D forms. But life on Earth uses almost exclusively L amino acids. Similarly, sugars in our DNA and RNA are D forms, not L forms. Why? No one knows for certain. Perhaps it's chance, frozen at life's very beginning on Earth. Or perhaps there's some deep reason, physics or chemistry that makes one form preferable to the other. But here's what's important: if you find organic molecules with predominance of one chirality, it's a strong sign of biological origin. Non-biological processes tend to produce equal amounts of both forms. Only life chooses one form and ignores the other. We can search for homochirality by studying light reflected from a planet. Chiral molecules interact with polarized light in special ways. If we could detect certain patterns in polarization of light from an exoplanet, it might indicate presence of large quantities of chiral molecules, possibly of biological origin. This is another strategy astrobiologists are considering. Not relying on detecting one specific molecule but searching for fundamental properties of life that would be universal. But all this raises a philosophical question. If we find something on another planet that satisfies all our criteria for life but works on completely different principles than Earth life, can we call it life? Or will it be something else, something for which we need to invent a new word? And an even deeper question: can life arise spontaneously from non-living matter? This is called abiogenesis, and it's one of science's greatest unsolved questions. We know it happened at least once, when life appeared on Earth. But how exactly did it happen? What was the sequence of events that transformed a mixture of simple chemical compounds into the first self-reproducing, evolving system? There are many hypotheses. Maybe it happened in a primordial soup, a warm shallow pond rich in organic molecules, where energy from lightning or ultraviolet light triggered chemical reactions that eventually led to life's emergence. Or maybe it happened in the deep ocean, at hydrothermal vents, where hot water saturated with minerals meets cold seawater, creating chemical gradients that could serve as energy source for first metabolic reactions. Or maybe life didn't start on Earth at all. Maybe it arrived on a meteorite or comet, seeds of life spread through space by a process called panspermia. This doesn't solve the problem, life still had to arise somewhere. But it expands the field of possibilities. Experiments have shown that many building blocks of life, amino acids, nucleotides, even simple proteins and nucleic acids, can form spontaneously under conditions we think existed on early Earth. The famous Miller-Urey experiment in the 50s showed that electrical discharges through a mixture of simple gases can produce amino acids. Hundreds of similar experiments have been conducted since, each adding pieces to the puzzle. But the transition from simple organic molecules to something we'd call living remains a mystery. This is called the origin of life problem, and it's one of science's great unsolved challenges. If this transition is easy, if it happens naturally under the right conditions, then life must be common in the universe. Where there's a planet with liquid water and an energy source, there should be life. But if this transition is difficult, if it requires an incredible coincidence of circumstances, a rare combination of conditions occurring only once per trillion planets, then we might be alone. Or at least very, very lonely. We don't know. And until we find life somewhere else, we can't know. A sample of one doesn't give us statistics. Only when we find a second independent example of life can we begin understanding how easy or difficult life's emergence is. And this is another reason why searching for biosignatures on exoplanets is so important. It's not just about finding someone out there. It's about understanding the nature of life itself. Understanding our place in the universe. Answering questions humanity has asked for millennia. We stand on a threshold. On the edge of a discovery that will change everything. Or perhaps on the edge of disappointment that will force us to reassess all our assumptions. Either way, it's a journey worth taking. The history of searching for life is full of false alarms. Moments of excitement followed by disappointment. This is part of the scientific process. We propose a hypothesis, test it, and if it proves wrong, we learn and move on. But each false alarm leaves a mark. A reminder of how easy it is to see what we want to see. How easy to interpret ambiguous data in favor of our hopes. In 1996, a group of scientists announced they'd found evidence of fossilized bacteria in Martian meteorite ALH84001. This was a rock ejected from Mars by an asteroid impact millions of years ago, which eventually fell to Earth in Antarctica. Inside this rock, researchers found tiny structures that looked like fossilized microbes. They also found organic molecules and minerals that on Earth are usually associated with biological activity. It was a sensation. The US president made a statement. News channels devoted hours of airtime to it. It seemed we'd finally gotten proof of extraterrestrial life. Not just somewhere in distant space but right in our solar system, on our neighboring planet. But with further study the evidence became less convincing. The bacteria-like structures were too small, an order of magnitude smaller than any known Earth bacteria. It was unclear whether something so small could contain everything necessary for life. The organic molecules might have been contamination from Earth. The minerals might have been produced by non-biological processes. Today the scientific consensus is that ALH84001 probably doesn't contain evidence of life. Possibly contains, the question remains open. But it's no longer considered compelling evidence. This was a humbling lesson. A lesson about how carefully we must interpret data. How high the bar of evidence must be when we claim something as extraordinary as detecting extraterrestrial life. Because extraordinary claims require extraordinary evidence. This isn't just a cliché. It's a fundamental principle of scientific method. When you claim something that radically changes our understanding of the world, you must provide evidence, leaving no room for reasonable alternative explanations. This was demonstrated again in 2020 when a group of scientists announced detection of phosphine in Venus's atmosphere. Phosphine is a molecule consisting of phosphorus and hydrogen that on Earth is produced mainly by anaerobic bacteria. It's a foul-smelling gas, toxic to most life forms, but its atmospheric presence could be a biosignature. Venus is the last place you'd expect to find life. The planet's surface is heated to nearly 500 degrees, enough to melt lead. Atmospheric pressure is 90 times Earth's. Clouds consist of sulfuric acid. It's hell in the literal sense. But at an altitude of about 50 kilometers, conditions are less extreme. Temperature is moderate, pressure close to Earth's. Yes, still sulfuric acid, but some Earth microbes can survive in very acidic conditions. Could life exist there, in Venus's clouds? The phosphine announcement generated enormous interest. If confirmed, it would be one of the most significant discoveries in astrobiology history. But doubts began almost immediately. Other teams reanalyzed the data and found the signal wasn't as clear as originally claimed. Perhaps it wasn't phosphine at all but sulfur dioxide or another sulfur compound. Or perhaps it was an artifact in the data, a result of how observations were processed. Subsequent observations with other telescopes couldn't confirm phosphine's presence. Or at least not in the quantities initially claimed. If phosphine is there, there's far less than initially thought. And even if phosphine is genuinely present, there are possible non-biological explanations. Perhaps it's produced by volcanic activity. Or by lightning in the atmosphere. Or by some exotic photochemical reactions we don't yet fully understand. Again, not conclusive proof. An intriguing possibility requiring further study, but not compelling evidence of life. This is a pattern repeating again and again in the history of searching for life. Exciting announcement. Wave of interest. Then skepticism. Reanalysis. Alternative explanations. And ultimately uncertainty. It's frustrating. We want answers. We want certainty. We want to know, are we alone or not? But science doesn't work that way. Science works slowly, carefully, gradually building evidence. Each observation is one puzzle piece. Each experiment eliminates some possibilities, opens others. Truth emerges not in one dramatic revelation but in slow accumulation of knowledge. And yet there are reasons for optimism. Despite false alarms, despite disappointments, we're making progress. Real, tangible progress. We now know planets are ubiquitous. Our galaxy has hundreds of billions of planets. Perhaps trillions. And a significant fraction are rocky planets in habitable zones of their stars. We know life on Earth is incredibly diverse and adaptive. It exists in conditions we once considered impossible for life. If life can thrive in Yellowstone's hot springs, in Antarctica's frozen lakes, in deep underground mines, then why can't it thrive on other worlds? We know life's basic ingredients, organic molecules, are common in space. We find them in molecular clouds, in comets, in meteorites. The building blocks are there. The question remains, do they assemble into something living? And we have tools to answer that question. For the first time in human history we have technologies allowing detection of biosignatures on exoplanets. We can study their atmospheres, search for signs of life. We can, in principle, answer the question, are we alone, empirically, with data, with evidence? This is an incredible time to be alive. We're witnessing a revolution in our understanding of the universe. And it's quite possible that in coming years or decades we'll make a discovery that will go down in history as one of humanity's greatest moments. The detection of life beyond Earth. Or, equally importantly, the absence of such detection after thorough searching. Because a negative result is also a result. If we study hundreds of planets, planets of all types, in different conditions, with different stars, and find no signs of life, this will tell us something profound about life's nature. It will tell us that perhaps life truly is rare. That we truly are special. That our existence isn't a guaranteed consequence of physical laws but incredible luck, a chain of improbable events that led to something unique. And that too would be a discovery. Profound and in some sense disturbing. Because it would make life on Earth even more precious. Even more fragile. Even more worthy of protection. It's called the Fermi paradox, after physicist Enrico Fermi, who reportedly first formulated it over lunch in 1950. If the universe is so large, if there are so many stars and planets in it, if conditions for life are so widespread, then where is everyone? Where are the aliens? Where are their ships, their signals, their civilizations? This is a paradox. On one hand, everything logically points to intelligent life being common. On the other hand, we see no signs of its existence. In our galaxy alone there are hundreds of billions of stars. Many have existed billions of years longer than our Sun. If even a tiny fraction of planets around these stars developed life, and if even a tiny fraction of that life evolved into intelligent technological civilizations, then the galaxy should have thousands, maybe millions of such civilizations. Some of them should be far older than us. Millions of years older. Billions of years older. With technologies so advanced they'd seem like magic to us. Civilizations that colonize their star systems, perhaps even their galaxies. That build structures the size of solar systems. That harness the energy of entire stars. Where are they? Why don't we see their traces? Why isn't the sky filled with their radio signals, their laser transmissions, their interstellar ships? This is the great silence. It's called the Fermi paradox, but it's more than a paradox. It's a mystery that questions our basic assumptions about life, intelligence, technology, the universe. Dozens of explanations for the great silence have been proposed. Each is disturbing in its own way. Each has implications for our future, for humanity's fate, for our place in space. One explanation is called the rare Earth hypothesis. Maybe life isn't as common as we think. Maybe requirements for complex life's emergence are so specific, so demanding, that suitable planets are extremely rare. Yes, planets are common. But a suitable planet is more than just a rocky world in a habitable zone. Perhaps you need a large moon to stabilize the planet's axial tilt and create stable climate over billions of years. Perhaps you need a giant planet in the outer system to deflect dangerous asteroids and comets, reducing frequency of catastrophic impacts. Perhaps you need the right location in the galaxy, not too close to the center where stellar density is high and radiation intense, but not too far on the outskirts where heavy elements are insufficient. Perhaps you need a certain history of geological activity. Perhaps you need plate tectonics to recycle carbon and maintain stable climate. Perhaps you need a magnetic field for protection from stellar wind. Perhaps you need a star with the right mass, not too massive to burn too quickly, not too small to be too active and unstable. Adding all these requirements together, some researchers concluded Earth-like planets truly are rare. Maybe there are only a few in the galaxy. Maybe we're alone or nearly alone. But even if suitable planets are rare, this doesn't completely solve the paradox. The galaxy is huge. Even if only one star in a million has a suitable planet, that still means hundreds of thousands of such planets in the galaxy. So maybe the problem isn't planets but life itself. Maybe abiogenesis, the transition from non-living matter to life, is incredibly difficult. Maybe it's an event so improbable it happens only once per trillion planets. Or per trillion galaxies. Or maybe the problem is intelligence. Maybe simple life is common, but intelligence is rare. After all, on Earth, life existed for billions of years before intelligent beings appeared. For most of Earth's history, the planet was populated only by microbes. Multicellular organisms appeared relatively recently. Animals even more recently. An intelligent, technological civilization, us, appeared just a blink of an eye ago on geological timescales. Maybe this is the norm. Maybe the universe is full of microbial life but intelligent civilizations are incredibly rare. Or maybe intelligence is common, but technological civilization is rare. Maybe most intelligent species never develop technology. Or develop it but abandon it. Or destroy themselves with it. This is a particularly dark possibility. The idea that there's something we call the Great Filter, some barrier, some challenge that most or all civilizations face, and few or none survive. Maybe it's nuclear war. Maybe it's climate catastrophe. Maybe it's artificial intelligence that goes wrong. Maybe it's biological warfare. Maybe it's something we haven't even thought of yet, some danger inherent in technological development that we haven't encountered but will. If the Great Filter is ahead of us, we're in trouble. It means the silence of the universe isn't because intelligent life is rare but because intelligent life tends to destroy itself. It means our future is precarious. It means we might not make it. But maybe the Great Filter is behind us. Maybe it's the transition from chemistry to life. Or from simple cells to complex cells. Or from unicellular to multicellular life. Maybe we've already passed the hardest part, and the rest is relatively easy. If that's true, we have reason for hope. It means civilizations that reach our level of development have good chances of surviving, of spreading through space, of becoming long-lived. There's another possible explanation for the Great Silence, one that's perhaps even stranger. Maybe they're out there, but they're hiding. Deliberately not making themselves known. Why would they do that? Perhaps there's some cosmic etiquette, some rule that young civilizations must be left alone to develop naturally. Star Trek's Prime Directive made real. Perhaps advanced civilizations watch us but don't interfere, waiting for us to reach some threshold of development before making contact. Or perhaps they know something we don't. Perhaps there's some danger in making oneself visible to the cosmos. Perhaps the universe is a dark forest, where civilizations that advertise their presence attract the attention of predators. Perhaps silence is survival. Or maybe, and this is the strangest possibility of all, maybe we are first. Maybe in all the vastness of the observable universe, with its hundreds of billions of galaxies, each containing hundreds of billions of stars. We are the first intelligent, technological civilization to emerge. It seems absurdly unlikely. Absurdly arrogant. But someone has to be first. If intelligent life is possible, then at some point, somewhere, the first intelligent civilization must have appeared. Why not us? If that's true, we bear an enormous responsibility. We are the seed from which all future intelligence in the universe might grow. Our choices, our actions, our survival, they matter not just for us but for the entire possible future of intelligence in the cosmos. These are heavy thoughts. Overwhelming thoughts. And we don't have answers to them. Not yet. But we're searching. We're building better telescopes. We're studying more planets. We're refining our methods for detecting biosignatures. We're sending probes to the moons of Jupiter and Saturn. We're listening with radio telescopes for any hint of artificial signals from space. Every year, we learn more. Every year, the picture becomes clearer, or sometimes more confusing. Every year, we get closer to an answer. And when that answer comes, whether it's the discovery of life on another world or the sobering realization that we might truly be alone, it will be one of the most profound moments in human history. We stand at the edge of this moment. Right now. In our lifetime. This isn't something our distant descendants might experience. This is something we might experience. You. Me. Anyone reading these words. The search for extraterrestrial life isn't just science. It's philosophy. It's existentialism. It's the most fundamental question we can ask about our place in the cosmos. Are we alone? Or are we part of something larger, something grander, a universe teeming with life and intelligence and wonder? We don't know yet. But we're finding out. Every observation, every measurement, every new planet discovered brings us closer to the answer. And perhaps the most beautiful thing about this quest is that the journey itself, the searching, the wondering, the gradual piecing together of clues, is as profound as any answer we might find. Because in searching for life elsewhere, we're also searching for ourselves. We're trying to understand what makes us human, what makes life special, what our existence means in the grand scheme of things. Every biosignature we detect or don't detect, every exoplanet we study, every spectrum we analyze, it's all data in the grandest experiment humanity has ever undertaken. The experiment to determine whether the universe is alive or dead. Whether consciousness is common or rare. Whether we have neighbors or are orphans. The tools we're building, the James Webb Space Telescope, the extremely large telescopes, the future space missions, they're not just instruments. They're our eyes and ears reaching out into the cosmos, searching for kindred spirits. For echoes of ourselves. For proof that this spark of awareness we call life isn't unique to one pale blue dot but is instead woven into the fabric of the universe itself. And if we find it, if we detect that unambiguous biosignature, that combination of molecules that can only mean life, that moment will be seared into human consciousness forever. It will be the moment we realized we're not alone. The moment the universe became bigger and stranger and more wonderful than we ever imagined. It will raise as many questions as it answers. What is that life like? How did it evolve? Is it like us or utterly alien? Is there intelligence there? Could we communicate? What would they think of us? But it will answer the one question that matters most. We are not the only planet in all the universe where chemistry became biology, where molecules organized into systems that could maintain themselves and reproduce and evolve. We are not a fluke, not an accident so improbable it happened only once in all the vast expanse of space and time. We will know that wherever conditions allow, wherever there's liquid water and an energy source and enough time, life finds a way. Life emerges. Life persists. And if we don't find it? If we search hundreds of worlds, thousands of worlds, and find nothing but silence? That too is an answer. A sobering, profound answer. It means we are precious beyond measure. That the earth is not just our home but perhaps the only home life has ever known. That the biosphere we inherited is not one of many but unique, irreplaceable, infinitely valuable. It means we bear responsibility not just for our own survival but for the survival of life itself. Because if we destroy ourselves, if we render this planet uninhabitable, we might be extinguishing the only flame of consciousness in all the cold, dark universe. This should terrify us. This should humble us. This should unite us. Because in the cosmic perspective, our differences, national, ethnic, religious, political, become trivially small. We're all inhabitants of the same small world, the same precious oasis in the desert of space. We're all made of the same atoms, animated by the same molecular machinery, products of the same evolutionary process. We're all siblings under the skin. Children of the same planet, the same star, the same cosmic event that created the solar system 4.5 billion years ago. And whether we're alone or one of many, that kinship matters. That unity matters. Because the universe is large and cold and indifferent. It doesn't care about us, doesn't care whether we survive or perish. The only thing in the universe that cares about humanity is humanity itself. So we search. We build telescopes and launch missions and analyze data and debate interpretations. We look for biosignatures in distant atmospheres and life in Martian meteorites and organic molecules on icy moons. We do this because we must. Because the question, are we alone, is hardwired into human consciousness. Because looking up at the stars and wondering is part of what makes us human. And because someday, maybe soon, maybe in our lifetime, we'll get an answer. That answer, whatever it is, will change everything. Will change how we see ourselves, how we see our planet, how we see our future. Will change philosophy and religion and culture. Will rewrite textbooks and recalibrate our place in the cosmic story. We live in incredible times. Times when humanity is taking its first tentative steps toward answering questions our ancestors could only dream about. When the tools of science have advanced to the point where the question of extraterrestrial life transitions from speculation to testable hypothesis. The revolution is happening now. Not in some distant future. Now. And we, all of us, are witnesses to it. Participants in it. Whether we realize it or not, we're living through one of the pivotal moments in human history. The moment when we transition from wondering if we're alone to actively searching for the answer. The moment when finding life elsewhere became not a fantasy but a possibility. Not a dream but a goal. This is the search for another world. The search for biosignatures on distant planets. The search for life beyond Earth. But more than that, it's a search for meaning. For context. For our place in the grand tapestry of existence. It's a search that might end in triumph or disappointment, in confirmation or confoundment. But it's a search worth conducting, regardless of outcome. Because in the end, what defines us isn't the answers we find but the questions we dare to ask. And this, are we alone in the universe, is the greatest question of all.